Okay, I think that we can start with the meetup. So just a few seconds. Okay, hello everyone. It is my great honor and pleasure to announce that we are back in business with the meetups and that we are going to have very experienced and cool guest today, and one of the founding members of Quantum Serbia initiative, and that's Petar Korponaic. Before I start with his announcement and what you're going to hear in this lovely meetup, I would just like to take 2 minutes of your time just to explain to you what you have been doing in the past few months and what are our plans for the future, just to get you sync with the whole Quantum Serbia initiative, which right now has more than 20 people active, and we believe that we can have even more than that. So basically, I would like also to invite you, if you're interested in, just write to someone of us. You can write to me as well, or Petar, Sasha, Ilya, whoever. Maya, there's a lot of us who are in this meetup group, so we can add you there. I can see a lot of you already being the part as Slobodan Cičić, for example. So basically, it is a cool thing to see you once again here. In the previous months, we have been doing what have we been doing as a meetup group and initiative. We have started to develop a further connection with academia as well as businesses. We suppose in the future, in the following months, we'll have the real product of that you can see some extraordinary things happening here in Serbia regarding this cooperation. We have also, with great help for the part of the professors and academics from the University of Belgrade Faculty of Physics, we had started with the introduction to the quantum part of the quantum computing. And what we are going to do in the following years, in the following, not years, but the following months, we are going to talk a little bit more about the machine learning part in the equation of quantum computing and computing as well. What have we also doing? We have started creating our Medium channel. We have started, and thanks a lot, Sasha, for that. We have established connections with IBM. We are looking forward to start connections with Microsoft and some other big companies. And what we are going to try to do in the 2022, we will see if that is possible. We really think it is possible to try to organize some kind of quantum hackathon. So we will see if that's possible. We truly do believe so, but let us see what will be happening. Beside that, what we are going to do, we're going to start building some kind of a library of knowledge for quantum computing and quantum itself, not only quantum computing, but quantum itself. And we are going to try to disseminate this one and to try to promote to the people and to make further connections with professionals, wannabe professionals, and enthusiasts in the field of quantum and quantum computing. So basically, that was what we were doing in the previous months. I would like also once again to call all of you to join us in our group, because more the merrier, and we will do much more things with with the same effort, and the results will be much faster and much better. So basically, if you have some free time, like a couple of hours per month or something like that, just join us. There's a lot of things that we can do together, if nothing else, just to meet each other and to try to develop quantum initiative in Serbia. With being said that, like I said, one of our founding members, Petar, if you're calling on English, it's Peter, but in Serbian, it's Petar. Korponaic, he's our dear friend, and he's going to talk a little bit more about hands-on quantum computing. In his talk, he is going to show us how to solve a simple problem with quantum computer. Basically, we are talking about preparing and coding input data, designing and running quantum programs, reading results, integrating and using quantum function, classical programs, etc. Basically, what is important to say is that Peter is founder and he's a software engineer and entrepreneur. He is founder of the Fantastica Finland. He's co-founder, as we said, of Quantum Serbia, and he's a mentor in Quantum Open Source Foundation. If maybe I'm wrong, I think that you are also in a QuizKit or not. If I understand, if I think correctly, you're part also of QuizKit advocate or not. I think that you are. Correct me, please, if I'm wrong.
I'm not.
Okay, but we have a lot of people in our group that became QuizKit advocate.
We have other member who is QuizKit advocates from Quantum Serbia.
Yeah, we have few of them, and Texas Sasha, a few of them right now. And what I would like to say without further ado, I would like to call Peter to share his screen and to start with his presentation for today. Thank you all.
Thank you, Alex. Let me share my screen. Host disable participant screen sharing.
Sasha, if I can just kindly ask you, there is a small white button in small white thing in the green button. You just need to click there and to give the permission to share screen to be better.
Peter, could you please try again?
Okay, looks like it will work.
Small technical difficulties, people, that happens all the time. So
no problem.
I'll mute myself and give you the floor.
Okay, thank you. So I will try to, I will keep this sidebar here with thumbnails. I will not make it full screen because I need that. I hope it's okay. Write into chat if it's not okay. Okay, so yes, as Alex introduced me, my name is Petar Korponaic. I'm running Quantastica. Quantastica is a startup from Helsinki, Finland. And our focus is quantum software. More specifically, we are making tools, programming tools for quantum computing, and our main focus is automated quantum algorithm development or automated quantum algorithm design. By the way, I can hear some background voices. Some smiling. No problem, as long as you smile. Okay. Yes. So today in Quantum Serbia, we already had multiple webinars, and most of webinars were more theoretical. And this time we decided to make one very practical webinar. And what we will do today, so today we will choose a simple problem that will be very, very simple problem. And we will make a program which will solve problem using quantum processing unit or quantum computer. And we will learn how to, so we will pass through the entire process, entire cycle, and we will learn how to encode data for QPU, how to make our own quantum algorithm. So we will make quantum algorithm with our own hands. We will not use existing algorithm. And we will learn how to execute program on simulator, noisy simulator, and on real quantum computer. And we will learn how to read and decode results returned from quantum computer. And all that will be integrated into classical program, which will use quantum processing unit. So this is the plan for today. Looks ambitious, but it will for 1.5 hours, but it's possible. So it's not that bad as it looks like. So let's go. So CPU plus QPU. So in similar way as today we have GPUs which perform certain tasks which are better suited for graphical processing units. In a similar manner, we will have a QPU or quantum processing unit, which will take some hard computational problems. It will so CPU will send that data to, or send data to quantum processing unit. It will process data and it will return results. So it's very similar approach. And in this picture, we have at the top side, we have a classical computer, and on bottom side is quantum computer. And in classical computer, we have some input data from, I don't know, user input file or data stream or whatever. And we need to encode that data for quantum computer. And because quantum computer doesn't have input port like digital computer has, so encoding data means that we need to make quantum program which will put quantum computer into state in which it has our input data encoded. So quantum computer starts or initializes in 0 state, and we will on the fly, when we receive data, we will encode that, and that means we will make quantum program which will transform 0 state into prepared state, into state in which quantum computer have data encoded, and we will run, and then main program executes. By the way, this execution of quantum program is single process, so we don't have this middle step here. I just added it here for illustrative purpose. So then main program executes, or main quantum algorithm executes, and transforms prepared state in which we have data, input data. It transforms that state into final state, into state in which we have result, and then this is then measured and decoded by classical computer, and decoded output is returned back. So we will pass through this entire cycle today. And let's go. So before we start doing something, for completeness of my presentation, we will not talk about theory, especially not about quantum physics. But I need to just to show some very simplified model of quantum computation, or how quantum computer is working from the perspective of software engineer, or for more for computer science perspective and less from physics perspective. So I need to first to explain what is state vector, because we will use that that word in a presentation. So let's see what is state vector. So quantum computer, the state of quantum computer can be described with a vector of probability amplitudes. So this is, for example, for 1 qubit quantum computer, or one single qubit, has 2 possible outcomes. So when we measure qubit, we can measure only single bit. So from 1 qubit, we output of 1 qubit is only 1 single bit, and 1 qubit has there is a probability of reading 0 or reading 1. So so the state of qubit can be described with this probability amplitudes. Probability amplitude is complex number. So when we are talking about state vector, we are talking about vector of complex numbers, and each number is one of possible outcomes, which absolute value when squared gives us probability. We cannot directly write, and also we cannot directly read amplitude. So this is something that we cannot access. We cannot directly read this state vector. All we can read from quantum computer is this single bit. So from 1 qubit we can read only 0 or 1 with some probability. This is just example state of a single qubit, which is in equal superposition, and we have 50% chance of reading 0 and 50% chance of reading 1 from it, and probability is always 100%. So this vector is unit vector. The sum of absolute value squared of state vector is always 1. So probability is always 100%. In 2-qubit quantum computer, we have 4 states. So we have two on n amplitudes. And from 2-qubit quantum computers, we have 4 possible outcomes. So we can read both qubits 0, first qubit 1, second qubit 0, first qubit 0, second qubit 1, and both qubits 1. So this is what we can read from 2-qubit quantum computer. We have probabilities, and we have 4. So we have 4 amplitudes. So this column, this amplitude column, is actually state vector. The other columns is what I shown here to be more illustrative and more readable. And in this case, again, we have equal superposition of all states, but we need to also to say that amplitude can also be negative number. So this is a complex number. So we have a real and imaginary part. It can be positive and negative. As I said, we cannot observe that, we cannot read that, but we can sample from quantum computer and read, and we can find the probability of this state. So probability is something that we can read by running program multiple times. So this is state vector for 2 qubits. Then for 3 qubits, similar. Now this is some again some example. With 3 qubits we can read all qubits 0, first qubit 1, other qubit 0, and so on. So this is 3 qubit state vector. It has 8 elements, and with 272 qubits, we can have as much number of possible outcomes as number of atoms in the universe. So this vector space is giant, and power of quantum computing is there. So with 272 qubits only, we can have a giant number of possible outcomes. So this is state vector. So it's important to think about state vector as a vector of complex numbers. So without any theory, without any physics and mathematics behind, this is all we need to know as for this presentation. And about measurement, so when we have some state, in this case, this is 3 qubit quantum computer, we have some state, and now when we read from quantum computer, we can read only one bit string, one of these bit strings. This is our outcome. And interesting and important to say is when we read from quantum computer, the state, the superposition is destroyed. So state vector collapses into into classical state, where we have 100% of probability of element that we read. So if we try to read again, we will get the same element. So quantum state is destroyed with single measurement. This is fundamental property of quantum mechanics. So this is not engineering limitation of quantum computer. This is something that we will never be able to change. So if we want to read this probability distribution, we need to put quantum computer again into same state, then read again, in which case we will read some other element, some other of this element, and repeat that many times, which is something that we call multiple shots. And in multiple shots, we make statistics of elements that we read, and then we can find what the probability distribution of the state vector. So this is important to say, so that that state vector is vector of complex numbers. We can read only one element from that vector, and not only element, we read only index of the element. So we cannot read the amplitude, we cannot read probability, and probability we can get only by sampling, and this is how we read data from quantum computer. Now, when we know what is state vector, I will say, let's see what is quantum program. So state of a quantum computer is, when we initialize quantum computer, we have initial state. So we have state vector at this left side. State vector is column vector. So we have that vector, and our quantum program transforms that vector into new state. So initial states is transformed into new state, and this is all that quantum computer can do. So there is no loops, there is no branching, there is no normal things that we from computer science use in everyday in programming. Quantum computer can only change state from one state into another state. And because probability is always 100%, so because this vector is unit vector, resulting vector is again unit vector. So the effect of this transformation is actually multiplication with vector matrix multiplication. And that matrix is unitary because it always need to produce unit vector. So effect of quantum program is actually the same as, so we can describe the quantum program as a unitary matrix. Now let's see example. So if we have some initial state, this is 2-qubit quantum computer. We have initial state. This is zero state. When you turn on quantum computer, it by protocol it initializes in a state in which we read zeros on both qubits. So we have 100% probability of reading 0 from it. And now we want to produce this final state, which is maximally entangled state or Bell state. But anyway, so we want to change state to 50% probability of measuring both zeros and 50% probability of measuring both ones. So this is our final state, and quantum program which transforms state from initial to final state is unitary matrix, which looks like this. So effect of quantum program is just we can imagine it as a unitary matrix. Now that quantum computer cannot execute any unitary matrix. Quantum computer, current quantum computers usually can run only 3, 4, or 5 instructions, or only 3, 4, or 5 different matrices. So if we want to run this on real quantum computer, simulator can do this. So simulator can take any matrix and then multiply amplitude, state vector with quantum program. We will get a final state. But real quantum computer has limited instruction set, similar to CPU, which has instruction set. The quantum computer has a limited number of matrices, unitary matrices that it can perform. So we need to decompose our quantum program into instruction set of the target quantum processor. And let's imagine, for simplicity, that our quantum computer, target quantum computer, can execute this Hadamard gate or Hadamard matrix and C0, for example. In that case, we can decompose this quantum program or unitary matrix into following matrices. Now, because this Hadamard matrix, this is just a name for the matrix by some scientist. So if we want, so because this is single qubit matrix or 2 by 2 matrix, we need to multiply it with identity matrix. This is Kronecker product, and then we have 4 by 4 matrix, which acts on first qubit, and then we have 2 4 by 4 matrices, which we multiply, and we get our matrix, which is effect. So which is effect that we want, and then quantum. So that quantum program, because it's hard to write matrices, people invented a handy way to display matrices, and quantum circuit is just these symbols in a quantum circuit are just short symbols for matrices. So, for example, this H symbol is actually this matrix, and this symbol is control not operation. So in this case, we have Hadamard on first qubit. We have identity gate here because we don't have any gate here, and we have C0 here. So this quantum circuit is just a more readable or human readable way to show quantum program, or to show to deal with these matrices. So this is quantum circuit. And quantum circuit, we can program, when we program quantum computer, we use a quantum programming language. Whatever quantum programming framework you use, or whatever quantum programming language you use, all you do is actually you are performing matrix multiplication with state vectors. So in this case, this is Hadamard on qubit 0 and control not, or CX control X on between qubit 0 and qubit 1. So this is quantum program. So programming quantum computer means playing with linear algebra. So we are playing with vectors and matrices. So this is what we do when programming quantum computer. Okay, so now we are ready. So let's continue and let's see what is our problem. So I choose very simple problem. I hope that you are not disappointed. We will calculate what is 2 plus 2 on quantum computer. and we will describe the entire process from zero to working program. Okay, so let's see. So at the top part, we have our problem. So it's A plus B equals C. A and B are operands, and this is our input data. So our classical computer will take that operands. It will encode it for quantum computer. So it will make state preparation program. That part will happen runtime. Every time we call the function with different parameters, with different arguments, we will make on the fly state preparation program. Then this operation is actual processing part is sum operation of adding numbers. So this is what our main program do. When input data is encoded, it will transform zero state into a prepared state where we will have input numbers encoded into state, and main program will transform that into final state, or where we have a result of addition encoded into vector, and then we will decode that. So we will read output from quantum computer, and we will decode that, and this will be we will return results. So this is what we will make now. Now question is which algorithm to use, how to encode input, and how to decode output. Now, if you Google, use internet, you will find that there is already quantum adder circuit, so you can use that. But let's make instead that let's see how we will make our own algorithm. So let's design our own algorithm for adding numbers on quantum computer. And now when we when you choose a quantum algorithm for your problem, then depending on which algorithm you use, there is different ways to encode input and to decode output. For example, algorithm. So this depends on how algorithm is designed. So this is how you will choose how to encode input and how to decode output. But because we are designing our own algorithm, then this decision is up to us. So how we will encode input and how we will decode output. And because this is very simple problem, and because we are dealing with integer numbers, I choose to encode data into binary form. So we will use binary encoding. So we will encode each bit of inputs into qubits. So for each bit, we will use 1 qubit. This is waste of qubits, but nobody will use quantum computer to add numbers, because this is much faster and much more accurate and much cheaper to do on classical computer. But for our small for this purpose, we will do it on quantum computer. So we will use binary encoding. Now we have input and output. We will make example data. So we will start 0 plus 0, where we encode first operand. So we encode operands in binary form. We join those inputs into single binary number. Why we are doing that? Because in quantum computer we have only single state. So state of quantum computers is just one single state. Some programming languages have quantum registers. So you can make two quantum registers and encode one input into one register, the second input into second register. But at the end, physically in quantum computer, it is happening into single state. So there is no two separate states in a quantum computer. So this is why we will encode both operands into single number, and that will be our input. And this is how we will expect to have output again in binary form. So we expect to have 3-bit output, and this is how output data will be encoded, and so then we know how we will decode that from state vector. So this is binary encoding. Now, how we will map bits to qubits. So as I says, for operand A and B, we will use 1 qubit per bit. So in first 2 qubits, we will encode operand A. On the second 2 qubits, we will encode operand B. And we will have 3 bits at output. You will notice that I added 1 more qubit here. On first look, it looks that this is not necessary to have 1 more qubit. So maybe we can use first 3 qubits as output, or last 3 qubits as output, and then that we don't need fifth qubit, but we need it actually because it's a long story why. But we need ancillary qubit. So we need to give it a space for calculation in very simplified words. So there is no unitary matrix which can transform these inputs, all of these input states into output states in this binary encoding if we have only 4 qubits here. So this is why I added 1 more qubit. So this is how bits are mapped, and this is quantum state preparation. Example for 2 plus 2, if we have 2 plus 2, we will have decimal 2 and 2, binary, this is 0, 1, 0, 1. And on first qubit, we will have no operation because qubit is already initialized at 0. Then on second qubit, we will have X gate. X gate actually puts qubit into state 1 or basic state 1. So it flips the qubit. This is similar to NOT operation in classical computing. And then for second operand, again, 0 and 1. And this is how our state preparation quantum program for state preparation will look like. So we will have X on qubit 1 and X on qubit 3. So this is how it will look like. And now it's time to code. So what we will do, we will convert both arguments into binary string. We will join binary strings into single string. Then we will take each binary digit from that string, and if it is 1, then we will apply X gate. And resulting circuit is state preparation block, or state preparation part of the program. Okay, let me now. I didn't prepare that. I mean, I didn't open notebook. Okay, before we start, just to show some prerequisites that I did. So I installed Qiskit. So we will use Qiskit because it's most popular, but the principle is the same. Whichever quantum programming framework you use or whatever brand you use, it's not important. So I installed Qiskit, and I installed our Quantastica Quantum Programming Studio API. We will need it later. And then I imported stuff required for this. Then I loaded IBMQ account and get the least busy quantum processing unit backend. And so this is some utility functions here. Not important, so let's not waste our time on this. But let's start doing our state preparation circuit. So this function, get state preparation circuit, receives our operands. It converts both into binary form. So we will have binary strings from A operand and B operand. Then we join that binary string into single string. So we will have binary input joined A and B. This is in okay. Then we convert that string to list of digits, and we will make new Qiskit circuit. So we will make new quantum circuit with 5-qubit register. So this is one 5-qubit quantum circuit. Then we iterate over digits. And if digit is 1, then we apply X gate on it. And at the end, I added barrier, which is when you draw a circuit, it will show as a vertical line. So it will divide our program to state preparation and main algorithm. This is just for cosmetics. Let's run this. It will take some time because it is waiting IBMQ to return backend. This is least busy quantum processor, but we don't need quantum processor for this part. So this part is purely classical. So we only create quantum circuit, but we don't execute quantum circuit yet. So our state preparation, this function actually returns assembled quantum circuit or quantum program, but doesn't execute it. So let's run this. And let's try if it works. Yes, it works. So for 2 plus 2, we have 0, 1, 0, 1. For, I don't know, 1 plus 1 is 0, 1, 1, 0, 1, 0. For 0, we don't have X gate. So this is, so our state preparation circuit, state preparation block is working. Okay, I will just clear outputs. Okay. Let me go back to the presentation. Okay, now we have this part. So this red part is now finished. So our we made function which takes input data, encodes that or makes quantum circuit with that X gates, which encodes input data in binary form into state vector. So we finished that part. Now we need to design main program or main algorithm. Let me go. So what is quantum algorithm? We need to find a circuit which is unitary matrix, which transforms each possible inputs into correct outputs. So it transforms input vectors into output vectors. So for example, if we have 0 plus 0, encoded into input vector. Output is vector which has 0 encoded into it. And if it's 2 plus 2, then we have a vector where we have 2 and 2 encoded into it. And output is a vector which has number 4 encoded into it. So we need to find single unitary matrix which solves each of these vector pairs. So when we multiply each of these vectors, this unitary needs to produce correct output vector. And this is single unitary matrix, which is decomposed to quantum circuit with gates. Now this part is hard to do. And what is normal way how people do this part? So first of all, people search for Google and see if there is already quantum algorithm which solves the problem. But we are doing it our way. Second way would be, for example, skilled quantum programmer will try to make first to make adder circuit for single bit inputs, and then to cascade that into multiple bit adder circuit. So if we have only 2 bits at input and 2 bits at input and 2 bits at output, then this is small circuit. It can work maybe with two qubits. Then this is small and relatively easy to make. And then you can stack that and make bigger adder in our case. But we will not do it. We will try to automate this process. So we at Quantastica, how we do it? We generate example data like this. So we generate input vectors and input and output vectors, which is training set. For us, this is training set, similar to machine learning. In machine learning, we have training set. We have inputs and expected outputs. In the same way, we can generate vectors for each input and for each output. And then we have tool which takes vectors and produces circuit out of it. So it reverse engineers quantum algorithm from example data. So this is what our tool is doing. So a little bit advertising for my company. So we call that tool quantum algorithm generator. And it also can accept matrix at input. If input is matrix, then it has effect of transpiler. So in that case, it only changes the instruction set to instruction set of your choice. And also input can be truth table. And in our case now, because this is a very simple problem, we will build truth table from our data. We will make truth table, and we will send that truth table to the generator, which will give us quantum circuit which solves this truth table. So this is how we at Quantastica do it. And so this is automated quantum algorithm design. It would be nice if I can talk how to manually, without any tools, to make quantum algorithm for this problem, but it will take more than our time for our presentation, and it will be boring to listen, more boring than this. And yes, so time to code. So what we will do, we will generate truth table from example for all possible inputs and all possible outputs. We will send that table to our algorithm generator, and the return circuit is our quantum adder or our main algorithm. So let's put hands on and let's try. So automatically design main circuit. So get main circuit function. It will build truth table from all possible inputs and all possible outputs. Our generator accepts input in CSV form. So this is why we are building, this is comma separated values. And in each line, we encode input into in binary form. We join that binary strings, and output is sum of numbers. And we build a truth table which looks like this. And then we use a quantastic algorithm generator to find circuit which solves the truth table. So we will execute QPS generator circuit from truth table. We will pass CSV, and we need to say what is the row of columns in a table. So first 4 columns is input, and last 3 columns is output. So this is required by function to understand what is input, what is output. So we have 4 columns input and 3 columns output. And when we run that, yes. So when we receive result from generator, it will be in QASM format. This is that quantum assembler format which I already showed you in a presentation. So this is QASM format, and from that we build Qiskit circuit, so quantum circuit from QASM string, and we return that circuit. So let me run this, make functional, and let's do it. So main circuit, get main circuit, and draw circuit. So we will draw it. We'll draw it and show. And this is returned by our generator. So this is our main processing block or main processing block of our quantum algorithm. So we have, for example, for 2 + 2, we have this state preparation block, and we have main circuit, which is the same for all inputs. We don't make main block for in every execution. We only make it once. So we made it, okay. And let's see what is next. So now when we have main block, so we solved this green part. So we have state preparation program, which executes every time when we call our function. It will every time make a new circuit. We need to join that circuit with main program and execute entire circuit at once, because quantum computer cannot do it in 2 steps. So this is only illustrative that we have this prepared state. So our classical part of our classical function creates state preparation program, joins it with prepared main algorithm, and then executes all at once and produces final state, which we measure and decode. Okay, so this is what we do now. And now it's time to integrate that and to decode, to see how we decode output. So our classical function I already said this. So we take arguments, we construct state preparation circuit, we join state preparation circuit with main circuit, we execute circuit, we decode output, and we return result. This is what we will make now. So this is time to code. So we will make quantum sum function, which will take A and B operands. I added some additional arguments here, which will be for our more educative purpose and more for illustrative purpose. But let's think about our operands. So we call out function that we earlier make, get state preparation circuit with these operands. Then we construct full circuit. We join state preparation circuit with main circuit. So full circuit is state preparation composed. This is Kiskit's function. And then we have full circuit. We add barrier, which is just a vertical line when drawing circuit. It also has use when compiling, but I added barrier just to be more fancy. Then I add classical register into quantum circuit. Classical register will accept our output, and this is 3-bit classical register, which I gave it name C. And then we measure qubit 2 into classical register 0, qubit 3 into classical register bit 1, and qubit 4 into classical register bit 2. So this is measurement part of the where we read outcome from qubit. So we read that bit string from quantum computer, and then we execute quantum program. I will show you this function. It was in the beginning. It was execute quantum circuit. I will show you that later. But let's focus now on summing numbers. So we execute full circuit, and then we decode output. We will execute. This function executes quantum circuit many times. 1024 by default in 1024 shots. And then we take most frequent outcome, because you remember that quantum computer quantum computing is probabilistic, so we get random one of the bit strings from quantum computer, and especially because quantum computers are noisy. If we have 100% of probability of reading correct output, it doesn't guarantee that we will get that outcome, because there is a noise. In quantum computers are noisy, and it's possible that it will return wrong result. This is why we execute it many times, and then we use most frequent output of the quantum computer, and then we simply convert that to integer because this is binary string. Output from quantum computer is binary string. We convert it to integer, and this is our result. So let's make this function, and then let's perform our sum. So A is 2, B is 2, quantum sum A, B, and print result. Let's go. And 2 plus 2 is 4. After 2 million years of evolution, evolved monkeys started using quantum mechanics for quantum computation, and now one evolved monkey is here to show you how to add 2 plus 2 on quantum computer, on super expensive quantum computer, but it was running on simulator. Also, let's try to be sure that this works. So 1 plus 2 is 3, 1 plus 1 is 2, 0 plus 1 is 1. So it looks like it works. Let's stay with our 2 plus 2. Yes, okay, so this is our quantum program. Now let's show some internals here. So let's make it fancy. And now we see the circuit which actually executes. So when we say 2 plus 2, it's 0, 1, 0, 1. Then we have main algorithm. This is those barrier instructions, those vertical lines, which only logically splits circuit into parts. We have main algorithm, which we made automatically using Quantastica algorithm generator. And we have a measurement gate here where we measure qubits into classical register, into 3-bit classical register. So this is our circuit. And this is histogram, which shows outcomes. In this case, I used a noiseless simulator, so it will give us perfect outcomes. So we have 100% of probability of measuring 4 at output. But I will add some noise. And now when we have noise, our outcome looks much different. Now, okay, we still have the biggest probability of measuring 4 at output, but we have dangerously close of reading wrong result. So if we make less counts or less shots, it's possible that that we will read 2 plus 2 is 3 or 1 or 0 or whatever. So quantum computers are noisy, and this is one of the challenges when designing quantum algorithm. One of the challenges is to make it resistant to noise as much as possible. So this is our challenges, what we are facing. And this is especially hard when we have many qubits. With more qubits, we have much more outcomes. With 20 qubits, we have 2 on 20 possible outcomes. And if you want to sample probability distribution for that, you need to make many counts or to design your algorithm differently. So this is noisy simulator. And why this circuit is so long now? So what is this circuit? I intentionally do this. So when we are using noisy simulator, we are actually mimicking real quantum computer. And real quantum computer cannot execute our these gates that we produced in our main processing block. So, for example, this is controlled not, or Toffoli gate. So this gate cannot directly execute on hardware. Also this one. So what is happening when you are running this on real quantum computer? Compiler transpiles, or compiler actually translates gates from circuit into set of instructions that can be executed on real quantum processor. In IBM quantum processors can execute X rotation around Z axis, so RZ gate, square root of naught, and control naught. So this is what is instruction set of IBM. I think all IBM quantum processors have this new instruction set. Before it was different. It was U3 and CX. Now this is instruction set. So program is not that short anymore. And if you have more qubits, and if you have, especially when you have more complex processing, not adding two numbers with quantum computer, if you have more complex processing, then this circuit becomes very long. And with each gate that executes on quantum computer, noise is added. So if this circuit is longer, then we will have even more noise here, and even less possibility of reading correct result. And then our program will return spam. So this is important to know that this is challenging in quantum computing when making quantum programs. Also, what you can notice, careful observer will notice that we have the qubits are remapped. So qubit 0 is here now. Qubit 1, qubit 2, qubit 3. So it's remapped. Why is that? Because quantum processor with this is quantum processor with 5 qubits. You cannot perform any operation on any qubit. This is additional difficulty when designing quantum algorithms. So coupling of qubits is not full graph. If you have control knot between qubit 0 and qubit 2, maybe those qubits are not connected. So maybe you cannot perform that between those two qubits. Simply, this is how quantum processors are designed. It's engineering problem. But compiler remaps qubits, and also where it's not possible just to simply remap, change indexes of qubits, then it adds swap gates which swap state of two qubits. And those swaps are these three C nodes, three C nodes all together. This is swap. So in this case, it swaps qubit 1 and qubit 3. Those two qubits are changed their states, because I guess it was required to perform this C node between these two qubits. So because this is not coupled on a real processor, it's simply swapped. So this is additional challenge when designing quantum programs. We need to think that quantum processor is not fully connected, and we need to have as less as possible multi-qubit operations, but this is hard to do. And now, now let's try to run this on a real quantum computer. And I will say a simulator. So not on simulator, but on real quantum computer. And if we are lucky, this will work, because IBM quantum computers are very busy, especially in this time, because now it's, but let's try if it will work. So now we are waiting for, we are actually waiting for quantum our quantum program is waiting in a queue, waiting for other users to finish tasks of other users to finish. And let's hope that we will get result. So this is not up to us. I'm not using paid account. We are using more AWS, Amazon Bracket, where we have paid account, but I'm using Qiskit for this presentation because it's much more popular, and I didn't want to confuse you. And this is why I am using free account, which, yes. So pretty long time to add two numbers. This is where we are today, after millions of years of evolution. It will not work. I will leave that program to run, so we will check later if it executed, and we will also have histogram and everything. So it will be interesting to show. But let's continue with my presentation. I have only a few slides left, so I'm in time frame. Not bad. So what are challenges of quantum computing? I show you this very simple problem. Maybe we can make another presentation with more suitable problem for quantum computing, because nobody will add numbers on quantum computer, but I hope it was illustrative enough. But let's just say what are challenges of quantum computing, why quantum computing is not applied to industry yet. So what is the problem with quantum computing? So we have two classes of problems. One problem is quantum hardware. We have limited number of qubits. We have a problem with qubit connectivity, this coupling, which I already talked about, executing gates between any qubits. We have a limited instruction set. So quantum computers can execute only 2 or 3 or 4 gates. So we need to disassemble our program or decompose our program into many gates. And many gates equal more noise. And one of the biggest problems is actually noise. This is why I have this exclamation mark in on noise. So noise is biggest problem. On this our simple and small problem, noise is not big issue. So we just take most frequent output and it works. But if you have bigger circuit and more gates in a program and more qubits, and this becomes very challenging to read anything useful from it. And this is one of the main, let's say, there are other problems as well, but this is most, let's say, most popular problems or biggest problems, especially noise. And in quantum software, we have problems which is algorithm design. It's hard to design quantum algorithm. And currently, today, we have only few algorithms which promise quantum advantage. So you will see many, you will see people, IBM organizing hackathons where there is thousands of participants. They are solving some problems, but most of those people are using actually existing algorithms. It's a rare case that somebody is making own algorithm to solve some problem. You will use Grover search or I don't know, Shor's period finding algorithm or something. So there are, but most of those exercises are done on small number of qubits. If you try to make some program which use 30 qubits, 40 qubits, 50 qubits, it's simply there is no algorithm which can do that on today's quantum computers. Why? Because, for example, people are speaking about some variational quantum algorithm which shows promises quantum advantage and so on, but that algorithm cannot run on 50 qubits. So, I mean, or let's say pure quantum algorithm where you have only quantum without that variational part, without optimizer, classical optimizer, pure quantum algorithm like we made it today. Algorithms for that often grows, the number of gates grows exponentially with number of qubits. So if you add, for example, in QFT quantum Fourier transform, which is very frequently used algorithm and the building block of many other algorithms. If you add more qubits, you are adding much more. With every qubit, you are adding much more gates into it. And on 50 qubits, you have so many gates, and the precision of controlling qubits needs to be very accurate in order to. So algorithm design is challenging. First of all, challenging. Second, it's challenging to make algorithm that scales. So this is the maybe essence of quantum software problems, is how to design algorithm which scales. Also, challenging is how to encode and decode data. As long as we are dealing with small number of qubits, it's easy to encode data. But how to encode data into 65 qubit quantum computer, because 65 qubit is vector which cannot fit into memory of classical computer. I'm not sure. I think that it cannot fit even into supercomputer memory. So this is 2 on 65 times the size of vector, but it's giant. So how you will encode data into that vector? So you need to have smart way to make that encoding part that we make here. Also, decoding data. Decoding data is challenging because that's sampling. Because when you read once, the state destroys. So you need to sample many times. And if you have many qubits, then your state vector is giant. And when so you need many times to sample from quantum computer to get some meaningful results. Also, decoding is challenging because noise is everywhere problem. It's problem everywhere. Yes, I said scaling to more qubits is challenging for quantum algorithms, and also there is a branch of quantum software which is playing with noise reduction. So there is a way to reduce noise using software, not only by developing better hardware. Of course, it's the primary goal to make hardware noiseless hardware, but you can also help from software side to reduce noise. And so what we at Quantastica do, so what is our approach? Our approach is to give hard jobs to robots. So this is always my motto. I hope that in the future I will not suffer from robots. Charge me for offensive words against robots tomorrow when robots became equal. But this is what we are trying to do. We are trying to use robots for these hard tasks. And what we do, so we do automated quantum algorithm design, and we have something which is quantum algorithm as a service. This is something that you cannot see on our website because this is available only for closed beta for our first users. One of our users was one of our early adopters was Oak Ridge National Laboratory from US Department of Energy, and they already published a paper in which they used our tool to find circuit for elementary particle simulation. So we already have some results, proof of that our tool is doing something meaningful. Also, we have machine learning based compiler. Actually, it's transpiler now, so we will soon have compiler. This is available. This is in alpha stage, and available demonstration is available on request. We produce shorter circuits than this. By the way, quantum computer executed. But let me just finish the sentence, and I will show you results. And we have productivity tools like we have a language converter between different quantum computing frameworks, different quantum computing languages. So, for example, we can convert IBM quantum program into Google Quantum Program or Microsoft Quantum Program. We also support Microsoft Q#, Rigetti, and other, also Amazon brackets. So we can convert between different brands of quantum computers. This is one of our productivity tools. We have a Quantum Programming Studio, which is drag and drop, easy to design quantum circuits tool. And we have everything integrated there into Quantum Programming Studio. So this is our approach to quantum software. And that's it for today, but I will show you just the results from real quantum computer. So yes, it calculated correctly, 2 + 2 is 4, yes. And we have, and this is histogram from real quantum computer. And as you can see, we almost finished with 0, with 2 + 2 is 0, you know. So it's this 0 outcome was dangerously high. With smaller number of shots, we could end with a wrong result. But okay, this is how quantum computers look today. Yes, that's it from me today. Thank you for listening me. I hope this was interesting. Let me see how many participants. Oh, we have 19 participants, including myself, I guess. So
we have 28. We had 38 in one part.
38.
So right now 28.
28. I see. Ah, yes, it's 19 messages in chat. Ah, okay.
Yeah, it was very cool. Cool thing. Okay, we have one question, and I would also like to ask everyone to ask a question. Ili ako baš vam je možda neprijatno na engleskom, možete i na srpskom postaviti pitanje, ja ću prevesti, nije problem. So the thing is, we have one question, and just give me a second to switch to where I have put it. So basically, one of the question was while you were running a code, it was the question that your solution is using IBM Q. And the question was, is there any other target platform for your software solution? Or do you maybe have plans to make solution more hardware agnostic?
Yes, our solution is hardware agnostic. I explained that later. I explained that later in the presentation after that question was asked. So I explained that we support many. Let me just share my screen for a second, just to show you one diagram. So yes, we are not married with IBM, like many startups are. So let me show you code converter, and this is what we support. So this is our platform. So whatever code we produce, all our tools support this quantum computing framework. So this is Qiskit from IBM, Qiskit and Qasm from IBM. Qasm is also can be imported and exported in many other frameworks. We produce PyQuil from Rigetti and Quill from Rigetti, Cirq, Google, Q#, Microsoft, Quest. This is Oxford Simulator Quest, Quirk, which is very nice tool. We have our own formats, and we have format. And there is one more format which is not shown here. It's Amazon bracket. So we also support Amazon bracket, but it's not shown here in this picture. So yes, we support many frameworks, not only Qiskit.
Okay, I think that. Okay, Michael, thank you for the show.
I was not sharing, so I was showing you something, but my screen was not shared. Okay.
Yeah. Okay.
Okay, is it okay to ask question this way, like by voice, or is it necessary to type?
No, it's totally okay to ask by voice. Right. It's even easier for me.
Okay, so thanks a lot. So I have a question regarding the probabilities once we have 3 qubits, right? So we had practically, when we had a single qubit or 2 qubits, we have this uniform distribution of probabilities of various combinations of qubits, right? So we had up, down for a single, and then this down, down, up, in up, up, equally like uniformly distributed. But then once we started having 3 qubits, I think it's a slide, one slide up from that one. Yeah, I was just, yeah, the rightmost table indeed. I was just wondering for the reasons why, say, the probability between the 0-0-0 combo and 1-1-1 combo is not equal, or in fact, why this distribution is not symmetric, so to say. Is there a particular reason why our probabilities as they are mentioned here?
Yes, yes. This probability doesn't necessarily be symmetric. So you can put quantum computer into any probability distribution. It was some log normal distribution. If you plot this, you will see something that looks like log normal. And this is the only reason why those two outcomes are very similar. So they are very close. This is actually not 0, it's a little bit more than 0.
Yeah, because it's rounded up, I believe it's like decimals are omitted, although they're presented here, I believe.
Yes.
So, yeah, but the reason is why there's a different probability for the, say, all down or all up qubit.
Why?
Actually, yeah.
Well, because we put it into that state.
Okay, so it's a prepared state intentionally generated to be so, right?
Yes, this is just some example, random example of some state where we, after execution of some algorithm, we can end it in this state, which is just an example. I mean, you can put it into any. But when you start quantum computer, it always starts in 0 state. So it starts in 0, 0, 0, 100% probability. This is 0 state of quantum computer. And this is some result.
The reason why I ask this is because I in a way assumed, although I'm not an expert at all, that perhaps this probability comes as such as a result of perhaps noise or perhaps even insufficient number of measurements. I mean, this is just like something that I temporarily assume. That's why I'm asking you this. But if you say this is prepared in this way to show these numbers, then it's fine.
Yes, I understand. You are careful observer. Okay. Yes, yes, it was just example.
Yeah. Anyways, yeah. Thanks a lot for the answers. Yeah.
You're welcome.
Okay, do we have an additional question, perhaps?
I have a question for you. Do you think that this practical approach is good to have in in future Quantum Serbia webinars? And also, how did you like my presentation?
This is a question for me for everyone, I suppose.
No, for everybody. So for everyone. So that's question for everyone. You can write in a chat, so we will take statistics from chat.
I think that people start reacting lovely. Okay, I can say personally that it was very interesting to see, like on this level, how the quantum computer is working basically, and basically when you got into details with a lot of graphs, I think that was very, very helpful to understand the basics.
Yes, my target audience when I was making this presentation was people coming from computer science, especially people who are not familiar with quantum computing yet. I guess that people from academia who are more into quantum physics, they look at my presentation like, very simplified caricature of quantum physics. But this is what how we at from software computer science, this is how we look at quantum computer. There is, of course, we of course know more than this, but I try to make it simplified enough for almost everybody. I hope it's not it's not offensive to or offensively bad.
It was good. It was good, really. Don't worry about it. Okay, so we have one question additionally. As C++ is Svi and noob when it comes to physics, I found it's open source SDK. It is, and you can find this is CQCL kit, and I'll share you with in a chat once again. The link. That seems, and the question is, that seems very fun to work on. So the question is, where do I start when it comes to learning about quantum computing to be able to work on something like this?
Yes, so where to start on quantum computing, it's hard to say. It depends on your, how to say, your background. If you are, and depends on where you see yourself in quantum computing. And so if you want to contribute to open source quantum computing project, maybe first, of course, you need to learn basics. Good way to start is Qiskit textbook. I'm not advertising IBM, but they have very, very nice tutorial there. So you can go from basics to advanced things. It's free, so you can, and it's also Jupyter notebooks with code examples which you can run directly. So it's very, very nice. I suggest you to start there, and then you will know where to go next. So you will see which books to take. I started about 5 years ago or 6 years ago. In that time, there was no that popular, that many popular literature from quantum computing, so I was forced to read scientific papers, and this is how I started. But of course, I found some books as well, and I was coding. The best way is to coding. So learning by coding, by making, learning by making. This is how I like to do. So
Okay.
Qiskit textbook, short answer.
Also, we have a question. I want to ask is in the beginning whether we had to have some tools as Qiskits prepared to follow this, but the example was quite good. Will the presentation and the example be shared with the participants? I suppose better. This will be shared. Okay, for sure. We had recorded the webinar, and we are going to post it on our YouTube channel.
Yes, I can also post the code, the Jupyter notebook that I used. The only limitation is that you need access to our tools to produce a main algorithm. So if you comment out that and just take the circuit, produced circuit, then the entire code will work. All you need to have is Qiskit. And if you don't have, if you are not our beta access user, then you don't need our tool. So Qiskit is enough to have installed to run my example.
Okay, I think that's it from the question side. So once again, I think that you have received like the dozens of thank you and a great presentation. I would like to just emphasize this fact. Thank you, Peter, for your, sorry, my brain just praise Peter for your time, for your knowledge sharing, and for contributing to the data, to the Quantum Serbia initiative. Thank you all once again, and you will get more information from us on the meetup group as well. Like I said, if somebody would like to join our Quantum Serbia initiative more deeply, just write to us and we will include you. That's an important last message. And once again, thank you all for coming and being active.
One more thing.
Okay.
I wish to, I have many, thank you, it was great, it was nice. I want to hear somebody who will say that it was not good and why. So leave into meetup group, write into meetup group. Okay,
that's an interesting thing. Let's see how that will end up. So thank you, or like I said, thank you once again, and see you soon. Okay, bye-bye.
Thank you. Bye-bye.